Okay, problem 1. We are sending a message using AM. So we'll say our normalized message is 1 kilohertz, so it's cosine 2 pi 1. I'll just write 1k for 1 kilohertz t. Our carrier frequency is 800 kilohertz. So with AM, we end up with the carrier frequency and we end up with sidebands that are the sum and difference of the carrier frequency with our message, which is 1 kilohertz. So the answer is C. Here's our carrier frequency 800, and then here's the lower sideband at 799 and the upper sideband at 801. If the question asked about double sideband suppressed carrier, there wouldn't be a component at 800. It would just be 799 and 801. Problem 2, if our baseband message has this range of frequencies, what is the bandwidth required for double sideband? Well, baseband looks something like this, so it's between 1K and 5K. And then I'll also write or show the negative frequency values minus 1K and minus 5K. So that's baseband. With double sideband, that whole thing gets shifted up to the carrier frequency and shifted down to negative the carrier frequency. If we looked at it at the carrier frequency, the positive carrier frequency, we'd see that the lowest frequency would be the carrier minus 5K. The highest frequency would be the carrier plus 5K. So then the overall bandwidth would be this, which is 10K. Okay, so for problem 1, I said a sinusoid, but then I wrote out cosine. So when I say sinusoid, I'm saying a cosine could be a sinusoid. I wasn't necessarily saying sine of 2 pi times 1,000 t. But that being said, even if this was our message, even if our modulator was cosine 2 pi 800 k t, you can work that out, look at some trig identities, you'll still end up with components at all 3 frequencies. And then problem 2, so m of t isn't just 1k. M of t is a sinusoid with a frequency of 1k. So it would be, and what I initially gave was cosine 2 pi 1,000 t. So there's the 1 kilohertz, and it's a function of time.